Stability of carbocation. Here we are speaking about the stability of different resonating structures. Earlier we spoke about the conditions of resonance, that is in what all situations the resonance can occur. Now resonance is occurring. The resonating structures are also called as canonical forms. One important point you have to understand is all the resonating structures that we are writing are only there on paper, which means they do not have any real existence. We are writing them. Why we are writing them? After observing a reaction, the attack of electrophile is taking place at different positions. How do you explain them? By the resonating structures. But what actually exists, you can say it exists in the form of resonance hybrid. It is more meaningful. But resonating structures we write on paper. So by a little practice, we assume that these are the resonating structures that are there for some certain ions. Now also these resonating structures, all of them may be equally stable, may not be equally stable. So which resonating structure is more stable, which is less stable? That is what we are going to discuss under stability of resonating structures. Now first I am taking benzyl carbocation to speak about the stability of the structures. What is benzyl? Benzene ring, next carbon atom is benzylic carbon. If there is a positive charge on that, this is benzyl carbocation. Now what are the different resonating structures we can draw for benzylic carbocation? Here, first what we can do is, there is a positive charge here. This double bond I am shifting it in this direction. That means we are giving a pair of electrons to that carbon. So this carbon, instead of forming a bond with this carbon, it is forming a bond with this carbon. So it is using its electron and the electron of this carbon together to give it to this carbon. So now a new bond is formed here and here. So in this process, this carbon lost its electron. This carbon did not gain, did not lose. Instead of sharing its electron with this, it is sharing with this. That is the difference. So this carbon lost its only electron. That is what is present here now. Is this point clear? So previously there is a positive charge. Now it has gained an electron. So thereby can I say the positive charge is nullified. So overall now we can easily understand by shifting of electron, that's it. So this bond shifted in this direction. So there is a loss here. So this is positive charge. So this is one resonating structure. Next, this double bond shifted here. So now the positive charge is here. This is nullified. You can see that. That is the second resonating structure. Now this bond shifted here. Positive charge here. A new bond is formed here. So this positive charge is nullified. This is the next resonating structure. Again this bond shifted here. So positive charge back on the carbon atom. A new bond formed here. This positive charge is nullified. This is the next resonating structure. If you look at overall molecule, 3 bonds are like this. Now they have shifted in this direction. That is the new molecule that is obtained. So all these 5 are the resonating structures. You can say 5 equivalent resonating structures are produced. All of them are positive charge on carbon atom. You can say 5 equivalent resonating structures are produced. What else you have to keep in mind is, if the resonating structures are more resonating structures, to form them more energy is spent. Can I say it that way? More energy is spent. If more energy is spent, overall energy of the system is lowered. So that means we have lower energy for the whole system. If energy is low for the system, what we can say, stability is high. So due to resonance, can we say stability has increased? That is the reason resonance is happening. That is the reason we are saying a concept that resonance is occurring. So overall in the entire process, net energy of the system has decreased. That is what is resonance. So thereby high stability. Is this point understood? Here we have how many resonating structures? 5 resonating structures. Here all the structures are similar because positive charge is on the carbon atom only. In some other case, all the resonating structures might not be similar. We will be seeing that case also. Positive. Now, let us see about the resonance of phenoxide ion with comparison with acetate ion. What is phenoxide ion? Oxygen having negative charge. So here, negative charge is on the oxygen. It is resonating. So it forms a bond here. That is this bond. Now this carbon cannot have 5 bonds, so automatically this pair shifts here, negative charge here. So what we are getting is a carbanion, that is a negative charge here. This shifts here. As a result, this carbon no longer can form one more bond. So this shifts here. So there is a negative charge here. So the carbanion, the negative charge either it formed at ortho position or now it is formed at para position. But it is never formed at meta position. Observe that. This negative charge shifts here. This carbon can no longer hold the bond. So this double bond shifts here. So a negative charge here. So now again it is back at ortho position. This anion again shifts here. So this carbon cannot have 5 bonds. So this double bond shifts here. You are going to get O minus. Again, how many resonating structures we got? 5. But keep in mind, in this 5 resonating structures, all are not equal. Sometimes the negative charge is on oxygen. Sometimes the negative charge is on carbon. Which can hold negative charge better? More electronegative atom can hold negative charge better. Which is more electronegative, oxygen or carbon? So electronegative atom holding negative charge is more stable structure than less electronegative atom holding negative charge. So all the resonating structures are not equal. So the earlier point that more resonating structures is more stability is not completely true. That is true when all the resonating structures are equal. Here all the resonating structures are not equal. Let us compare that with acetate ion, CH3CO minus. Here there is a negative charge. This is shifting here. Automatically this double bond shifts here and you are getting one more resonating structures. Are these two resonating structures equal?
Yes.
Exactly equal. So these two are equivalent resonating structures. Number of resonating structures are less, but they are equal. So if you ask which is having better resonance, phenoxide or acetate ion, I have to answer it as acetate ion because both the resonating structures are equivalent resonating structures. Is this point clear? So more than number of structures, having equivalent structures is more important in terms of delocalization, that is spreading of charge. So charge is being spread like this, the pike load is being spread like this equally. That is what we are showing by resonance hybrid. Here also pike load is being spread, but mostly it is concentrated more towards oxygen, you can say it that way. Wherever negative charges are there, we are showing by partial negative charge. How can we justify that this is true? We can justify that based on the acidic character. If I take phenol, that is phenoxide ion attached to hydrogen, you can H+. Phenol will dissociate into phenoxide and H+. Acetic acid will dissociate into acetate ion and H+. If the conjugate base, that is the anion, is more stable, H+ will not attack. Out of these two, H+ is attacking phenoxide more than acetate ion. That means more H+ is remaining in the solution here. That means this is more stable. Because H+ will attack if negative charge is there, but negative charge is undergoing resonance and delocalization. So H+ will not know where to attack. So it will remain as in the H+ in the solution. So acetic acid is stronger than phenol. So that is a proof that acetate ion is more resonance stabilized. That means equivalent resonance structures are more important than more resonating structures. That is what we are understanding under the point of stability of resonating structures. Is that clear?